Assalamualaikum and salam sejahtera. My name is Muhammad Azri Awang from Universiti Malaysia Sabah, Faculty of Food Science and Nutrition. So today I am pleased to share my research title on innovative microwave drying approach for enhancing the quality of indigenous herbarium, the case of Etlingera coccinea. So this study highlight how advanced drying technology can be applied to improve the quality and value of indigenous herbal resources. For the introduction, this plant, known as Etlingera coccinea, which is from the Zimberaceae family, traditionally a remedy treat for the stomachache, gastric problem, and wound healing. So this plant rich in phenolic compound, which is high antioxidant activity, and then others compound reported in this plant such as flavonoid, tannin, saponin, and steroid. So this why I interest this plant, because this plant is underutilized plant and then still using the traditional drying method, and then also limited data in on bioactive compound of this plant extract. In this study, we apply microwave drying, a modern technique that offers rapid and efficient dehydration. So the mechanism works as follows. Microwave energy is primarily absorbed by water molecule within the rhizome. This leads to internal volumetric heating through dipole rotation and ionic conduction. Rapid on the heating regenerate water evaporation and vapor pressure build up, so the moisture migrate from the inner tissue to the surface. So finally, the vapor escape from pore, resulting in fast and efficient drying. For the methodology, we have a three-part. The first one is check on the kinetic study. The second part, which is check on the physical analysis, which is include the water activity, color, and morphology. So the last one, which is check on the chemical quality, including TPC, TFC, and on antioxidant activity. For the result and discussion, we can see on the effect of microwave power level on moisture ratio, as shown in figure 1. The result shows that increasing the microwave power level significantly reduced the drying time of Etlingera coccinea rhizome. At 600 Watt, the shortest drying time was achieved, requiring approximately 1,200 seconds. But at 100 Watt, the drying process was much slower, taking up to 4,800 seconds. This behavior can be explained by the highest microwave power delivering greater energy penetration, which enhance internal volumetric heating and accelerate moisture evaporation from the rhizome tissue. Similar trend has been reported in previous study, where highest microwave power level was shown to improve drying efficiency and reduce processing time. For the figure 2, the drying rate of Etlingera coccinea rhizome was limited by internal moisture diffusion rather than surface evaporation. A peak drying rate was observed at 600 Watt, which was approximately 5 times higher than 100 Watt. This indicates that highest microwave power levels are more effective in overcome the internal resistance to moisture movement within the rhizome structure. So, as a result, enhanced internal heating at highest power level accelerate moisture transfer from the inner tissue to the surface, leading to a substantially highest drying rate. Next, figure 3, figure 4, and table 1 represented the effective moisture diffusivity and activation energy. The result showed that highest microwave power level increased the effective moisture diffusivity of the rhizome. At the highest power, water viscosity decreased while internal vapor pressure increased, creating a pumping effect that rapidly drives moisture out of the tissue. So, the activation energy for moisture diffusion was determined to be 4.15 watt per gram, representing the energy barrier that water molecule must overcome to migrate through the rhizome matrix. This relatively low activation energy indicates that microwave drying effectively facilitate moisture diffusion, particularly at highest power level. After that, in this study, 5 thin-layer drying models were evaluated, namely Lewis, Henderson, and Fabris, Page, Logarithmic, and Medley and Kuchuk model. Among these models, the Page model demonstrates the best overall performance in describing the drying behavior of Etlingera coccinea rhizome. So the statistical performance of each model was evaluated using the coefficient of determination, root mean square error, and chi-square value as summarized in Table 2. All the models exhibit R-squared value above 0.9, indicate a strong correlation between the predicted and experimental moisture ratio. However, the Page model showed that highest R-squared and lowest RMSE and chi value that confirm its superior predictive capability, consistent with previous findings reported by Zhang et al. 2022. For the physical quality of dry Etlingera coccinea rhizome was evaluated using 3 key parameters, which is water activity, color, and morphology. For the water activity, in Table 3 showed the water activity reflect the free water available for microbial growth and self-stability. At low power, 100 until 300 watt, water activity remained high due to case hardening, where a surface crack trap moisture inside. But at high power, 450 until 600 watt, water activity decreased significantly, approaching safe level. This reduction is due to the puffing effect, where internal steam rupture the crust, creating a porous structure that facilitates moisture release. It can conclude that high micro power improve water removal and stability. For the Table 4, microwave drying caused significantly change in the color of Etlingera coccinea rhizome. So compare the fresh sample, low dried sample at 100 were darker with slightly lower redness and highest yellowness, indicating browning and color loss. So as a microwave power increased to 300 until 450 watt, lighting improved and the color shift closer to the fresh sample, showing better preservation. So lastly, at the 600 watt, lightness decreased slightly, suggesting slight over drying effect. So for the overall color analysis, show that moderate to high micro power 300 until 400 watt maintain color close to fresh sample. For the surface morphology of Etlingera coccinea rhizome, dry at different microwave power level, was evaluated using SEM as shown in figure 6. At 100 watt, the Ryzen exhibit a compact shielded structure with intact cell wall and no visible pore due to the slow motion evaporation and low internal vapor pressure. But increasing the power to 180 watt initiate a matrix loosening with visible gap between cells, indicating the start of internal expansion. For the at the 300 watt, the Ryzen developed a fluffier porous structure with depth cavities, reflecting the puffing effect, where internal steam pressure exceeds diffusion, so facilitating moisture migration without collapsing the matrix. But for the at the 450 watt, cause a more pronounced cell wall rupture, then forming large channel that enhance drying rate but partially compromise structure integrity. So the lastly, at 600 watt, the microstructure show several collapse and honeycomb cavities, maximizing moisture release but risking thermal degradation of bioactive compound. From the figure C, we can see that the medium power 300 until 400 watt produce the most favorable microstructure, balancing efficient drying, matrix preservation, and enhanced solvent penetration for the subsequent extraction of bioactive compound. For the chemical quality analysis, we check on the TPC and TFC of this plant. So we can see on the figure 7, the TPC and TFC of Echinacea coccinea increase with micro power, reaching a maximum at 450 watt. This increase is attributed to enzyme inactivation at moderate power, which have preserved bioactive compound. However, at 600 watt, both TPC and TFC decrease due to the thermal degradation. Judging from the result, 450 watt is the optimal microwave power for maintaining bioactive compound during drying. So lastly, we check on the antioxidant activity, including the PPH, ABTS, and FRAC assay. So the antioxidant activity of Echinacea coccinea rhizome was strongly influenced by microwave power. The DPPH assay showed an increase in scavenging capacity from 87.36% at 100 watt to a peak of 93.74% at 450 watt, indicating enhanced free radical neuralization. Similarly to ABTS assay, demonstrate a 32% improvement in radical scavenging from 100 to 450 watt. So this further confirms that superior antioxidant potential at medium power level. So lastly, the FRAC assay show that a remarkable 6-fold increase in reducing power, which is rising from 270.7 milligram equivalent to trollop per gram at 100 power to 1655.1 mg equivalent trollop per gram at 450 watt. So this show that the improvement in electron donating capacity. This result indicate that 450 watt represent the optimal microwave power as it maximize antioxidant activity, while highest power may cause thermal degradation of sensitive compound. Judging from the result, we can conclude that the page model is the best model for Android Kinetic, and the physical and chemical quality the best at the power of 450 watt. Thank you for your attention.